Ioannis Prapas and Spyros Kondylatos are two PhD researchers that focus their investigations in forecasting wildfires. They have done many researches in this topic, and now we are going to analyze one of the papers they published along with other collaborators. Even though at a first glance it might seem like there is no relation between time series forecasting and wildfire risk prediction, we will later see that it has a lot in common. Wildfires are a global problem that destroy ecosystems, endangers human lives, and makes millions of euros of losses yearly. With climate change increasing wildfire risks, accurate forecasting is more critical than ever in order to help fire brigade officials effectively allocate their forces. Traditional methods, like fire danger rating systems, rely heavily on meteorological indices such as the Fire Weather Index, FWE. While useful, these models often overlook other vital factors like vegetation, topography, and human activity. Moreover, they typically lack the fine spatial and temporal resolution needed for effective forecasting. Therefore, the authors generated a data set with the aim of training predictive models, covering Greece from 2009 to 2020. This dataset, or data cube, integrates multiple layers of information. Weather data, variables like temperature, wind speed, and precipitation. Satellite data, features such as vegetation indices and land surface temperatures. Static data, topographical information and human activity indicators like population density, road networks, and surface altitude. Historical fire data, burned areas and their ignition dates. The data was harmonized into a 1 kilometer by 1 kilometer spatial resolution and 1 day temporal resolution covering Greece from 2009 to 2020. Each spatio-temporal box had the earlier explained features, and the target variable is whether a fire larger than 30 hectares occurred in that box or not. Therefore, this is a classification problem. However, this is a highly imbalanced classification problem. Fires are rare events. Most locations at most times experience no fires, and those that do are rarely larger than 30 hectares. In a similar study, estimating next day's forest fire risk via a complete machine learning methodology by Alexis Apostolakis et al., it was found that there is 1 fire instance every 100,000 no-fire instances. To address this imbalance, the authors of the paper we are analyzing undersampled the majority class and ended up with just 2 times more no-fire instances than fire instances. The resulting dataset comprises 18,354 instances, of which 12,430 are no-fire and 5,924 are fire instances. 4 different models were trained and compared: a random forest, a long short-term memory, LSTM, a convolutional neural network, and a convolutional LSTM. The first one was fed with just information of individual pixels in specific days. Therefore, the random forest model does not have any temporal or spatial information. The LSTM model, however, uses each pixel's last 10 days information as training inputs and predicts the following day's fire probability. The CNN model is designed to capture spatial context by analyzing 25 by 25 pixels variables. And predicts the center's pixel's next day fire probability. The ConV-LSTM model takes this a step further by combining both spatial and temporal contexts. For each pixel, it processes 25 times 25 neighboring pixels around the main pixel over a 10-day period. Now that we have talked about what models they used, it's time to talk about how they prepared the data for training. Due to the way the data cube is constructed, a big fire can generate lots of different fire instances in the training dataset. Therefore, using the traditional cross-validation scheme would be wrong. The same fire event could have some fire instances in the training set and others in the test set. This would be data leakage, since those instances would have practically the same feature values. In order to avoid that, they applied a time series scheme. They trained during the years 2009 to 2018, validated in 2019, and tested in 2020. This is really important, as they say. Fire prediction should be treated as a forecasting task. That is, to train the models in the past to predict the future. If it is not done this way, and the testing set is taken randomly, it overestimates the model's real capacity. This is not the only work that uses this technique. In the work by Alexis Apostolakis et al. We mentioned earlier, they also apply a time series validation scheme for wildfire risk forecasting. However, they use the time series cross-validation scheme. They partition the data into training and validation sets by sequentially sliding a fixed time window across the dataset, with the window expanding in size during each iteration of cross-validation. For instance, their approach involves training the model using data from 2010 to 2013 and validating it on 2014. Then, training on data from 2010 to 2014 and validate on 2015, followed by training on 2010 to 2015 and validating on 2016, and so on. This iterative process ensures the model is evaluated on its ability to generalize to future unseen data. After training the models, they measured them using precision, recall, F1, and AUROC, mentioning that the AUROC is the most important metric for the evaluation. The ConV-LSTM achieved an impressive area under the receiver operating characteristic curve of 0.926, outperforming the other models. This highlights the importance of incorporating both spatial and temporal contexts in wildfire danger forecasting. The LSTM, which only considers temporal data, and the CNN, which only leverages spatial information, both performed well but did not achieve the ConV-LSTM performance. Meanwhile, the random forest, which lacked these contexts entirely, had the lowest performance in most metrics, emphasizing the limitations of traditional approaches. One important conclusion that they mention by analyzing the performance of the LSTM and CNN is that temporal context is more important than spatial context. But numbers alone don't tell the whole story. To truly understand the value of these models, let's look at the fire danger maps they produce. The ConV-LSTM model generates detailed, high-resolution predictions that align closely with observed fire events. These maps not only surpass traditional indices like the Fire Weather Index in granularity, but also provide more realistic patterns of fire susceptibility, which can be critical for operational use. So, that wraps up this exploration of a study on wildfire forecasting by Ioannis Prapas, Spyros Kondylatos, and their team. This work demonstrates how advanced deep learning methods, like ConV-LSTM, can improve the way we predict and manage wildfire risks. Employing spatial and temporal data, they've provided a powerful tool for making more accurate and useful forecasts.